Okay, good afternoon. So today we take this time to have a revision on the average and effective values as well as the constant numbers, which we will use to analyze the sine, cosine waveforms. So in the lectures, we just simply learn about the effective values, and also we mention about the constant numbers. But today here, we're showing you two sessions about the basic theories on the average and effective values, as well as the constant number. So the first one is about the average and effective values of theoretical functions. As I just mentioned in the lectures, that in the single phase AC circuit, the current and the voltage to be analyzed is theoretical functions. Okay, so in theoretical functions, as the sine waveforms, so it has a so-called period. You can looking at the figure B1 here. Okay, B1 here. That for the first figures at the left, it is the sine waveforms. The T here represent the period. Okay, the period may be in times. Okay, and it may be so a period of times, or in the angles, may be by a period of angles. Okay, so this is one of the waveform that with a period of the t. So then its average values. In general case, the theoretical functions with a period t, the general theoretical function with a period t has average values given by the integration, instant values of the integration over one period and divided by the period. So okay, this is the general definitions of the average values of theoretical functions. Okay. So, however, for sine waveforms, if you use a Citrus definition to calculate the average values, we have found that average values over one period will be 0. So therefore, okay, in AC circuit, for sine or cosine waveform, current or voltage. Okay. We define the half. We define its half period average values, as the average value. Okay, so although, as I said, although generally that the average values of theoretical functions is defined as the average values over one period, in our case, in the AC circuit, for a sine or cosine waveform current or voltage, right? We define its half period average values as the average values. So what does it mean? So that means we using here, okay, P over 2 instead of T in AC. So, okay. So what happened to it? So anyway, so the in the AC circuit for a sine or cosine waveforms of the average or current, so we already define the half period average values as the average values because the whole period values, average values will be 0, right? As you can see here, be 0. So therefore, okay, for our cases, not T, but T, okay, we okay. So in our AC circuit, okay, we take the half of the period instead of the whole period T in our AC circuit to do the calculations of the average values. Okay, so one can write using these definitions to prove that for a sine or cosine waveform, okay, so sine or cosine waveform, the average values in half period will be the peak values times pi over 2. Okay, sorry. Okay. You can calculate the average values for sine waveforms during the half period. Okay. So that's the average values. That's the difference between our average values as the general average values defined in the some books for the theoretical functions. Here also there are some examples that using the definitions to calculate the average values. So the example 1, A1, so giving the theoretical functions, okay, and then you can estimate the average values using the definitions. Okay, so this is just a game of the mathematical calculations. You can do as more as you like. But remember that in the AC circuit, we just use the half period of it. Okay, so which we showed you about the results in the lectures. Okay, this is the average values definitions of it. And the second point is the so-called root mean square values or effective values. So what's the definition of it? Here, there is detailed descriptions. So the instantaneous powers in a resistor is given by the powers T equal to I, that's the current square times the resistance R. So resistance R, the current IT which changes with times. So the instantaneous powers is the I squared times the resistance R. So the theoretical current, okay, is said to have effective values or root mean square values, I effective or I root mean square. So if a constant current of that value would result in the same average powers as the theoretical current. So that's the definition of the effective current. So thus, we say that the effective values or root mean square values I squared times the resistance is equivalent to the average powers over one period of the theoretical current. So this is the average powers over one period of the theoretical current. Okay. So furthermore, you can find out that the root mean square values related to the average right powers over one period, the root square of the average powers. So this is the original definitions of the root mean square values or effective values, related to the power issues. So such a definition, of course, can also be applied to the voltage issues. Voltage issues. So similarly, you know that the voltage root mean square values if you have theoretical, right? Okay, voltage 0, that the period is T. Okay, so you know that the voltage will change with times. And the square of the voltage square of voltage, right? Over T. The instantaneous powers that related to the voltage is the V square over R, right? Okay. So this is the current, effective current issues. This is the effective voltage issues. Actually, they are similar, right? So the two sides has the R can be cancelled, right? So therefore, we will find the similar, right, definitions of the root mean square voltage. Okay, we find that root mean square voltage, the similar, that to the currents. Okay, so this formula is applicable to both the root mean square voltage or root mean square currents, both related to the power issues. In the AC circuit, we consider about a theoretical current or theoretical voltage. So the root mean square values is defined like this. So here we're showing you the detailed or fundamental definitions of the root mean square values or effective values, which actually depends on the power issues. Okay, So the term root mean square, from which the letters root mean square are taken, serves as a reminder how the root mean square values is obtained. Okay, so the root mean square values take the root of the mean of the function squared. Okay, take the root of the mean of function squared. The general periodic function yt as the effective values can be like this. This is the general definitions of the periodical function. So if you have periodical function, general function yt, then its effective values is defined like this. So in practice, you may have various types of the periodical functions. For each of the periodical functions, so you can using these definitions to calculate the effective values, or root mean square values. It's related to the amplitude of the periodic functions in different way, not always the same. Okay. Or sine or cosine waveform, the root mean square values root square value is related to its amplitude, by a factor of root 2. So for general functions, the root mean square values, the root mean square values, root mean will equal to the peak values over okay. So for a sine or cosine waveform, suppose that the amplitude of the waveforms is ym maximum values, then its y root mean square values is the peak values ym over root 2. This is applicable to all kind of the cosine and sine waveforms. Remember this one. In practice, as we just mentioned in the lectures, that we may have the harmonics in a circuit. It not just has the fundamental components. We may have the DC components. We may have the fundamental components. We may have the second harmonics, the third harmonics, and so on. Then, so the waveforms can be written into a series, as mentioned here, trigonometric series, trigonometric series. So, for example, so the yt equal to a0 plus a1 cosine omega t plus a2 cosine 2 omega t, and so on. The a0 is represent the DC component. The a1 cosine omega t represents the fundamental component. And a2 cosine 2 omega t represents the second harmonics, and so on, the third harmonic, the fourth harmonic, and the fifth harmonic. This is the cosine component. And meanwhile, it may have the sine component. Okay, so the b1 and sine omega t, b2 sine 2 omega t, and so on, represent the first and second harmonics respectively of the sine components. In such a way, its root mean square values, again here is the DC component. The DC component is the DC, right? Which is very straightforward. The DC component square and the half of the AC component square and the sum of all weight. Okay. What's happening? Okay. So for a series of the waveforms, which is a combination of various harmonics, its total effective values given by these formulas. If you just has one component, look at here. So if you just has the DC component, then it is just the A0. If you have no DC component, just have the one component. For example, just have the cosine omega t. So it will be A1 over root 2, right? A1 over root 2. Okay, just like this. So anyway, so based on these right definitions, you can calculate whatever waveforms root mean square values, whatever waveforms effective values. So this is the general definitions of the effective values for waveforms that changing with times. Theoretical functions changing with times. Okay. So that in our lessons, we just touch about the sine or cosine waveforms, just one sine cosine waveforms. Root, right? Root 2. Okay. No. Okay. This is for the function in do not confuse, right? Okay, so the example A4 is for the waveforms showing in figure A3. It is not a complete sine waveforms. Okay, so do not confuse it. Okay. For the cosine or sine waveform, complete cosine or sine waveforms, in our cases, the root mean square values related to the peak values is by factor root 2. Remember this one. So that's what we talked here. Okay. Okay, so not confused. For different period, so for different theoretical functions, the average values different periodical, right? The root mean square values is related to its amplitude in different form for the complete sine or cosine waveform the root mean square value is related to its peak values value by a factor of √2. Okay, so here is right some general equations, okay, but when you apply to the complete, right, okay, sine and cosine waveforms, okay, so the root mean square values will be the peak values over √2. So that's the base of it. Okay, for sine and cosine waveform, root mean square is this one. And furthermore, if you have waveforms, that is a combination of DC, that's A0, A0 represented here, and A1, A2, A3 represent the fundamental cosine waveforms, the second harmonics, the third harmonics, and so on. Then the root mean square values is related to the DC component A0 and the cosine component, right? A1, A2, A3 like this. So here is the general definitions of the root mean square values or effective values for a series of the sine cosine waveforms. Okay, remember this one. So, so in these chapters, so we just study about sine or cosine waveform, just one sine or cosine waveforms. Okay, so it is easy to understand that the root mean square values is the peak values over the √2. Okay, that's this one. √2, this one. So here, this appendix gives you the general cases. Okay, do not confuse of it. Okay, so now you should understand about the root mean square values or effective values. Okay, so the different theoretical functions has different forms of the root mean square values in terms of their amplitude. Okay. Okay. So we also learned about the complex number forms. So the complex number systems. So in practice, as you learn that, okay, so we can use one single right figures to represent parameters. Or in some cases, we have to use at least two figures to represent one parameters. For examples, for the AC current, it has the amplitude, it has the time period. So we have to use at least the two right parameter to describe it. And also for the resistance or impedance in the AC circuit, it has the resistance, it has the reactance. So how to describe the combination of the resistance and the reactance? So we should use a two-dimension system to describe it. A general two-dimension system is the XY plane. XY plane. So as shown in the figure B1. So if we have one point in the XY plane, so the horizontal axis is X, the vertical axis is the Y. Then we can describe one point here is the Z, okay, one point, okay. So Z6, okay, in the point. Okay. So we have different points, okay. So we have the Z1 point, Z2 points, then 3 points, then 4 points, then 5 points, okay, then 3 points, then 4 points, right? We have several points, okay, several points. So for each point, it has a projections on the x, right? On the x-axis and on the y, okay, x. For example, for the Z4, as we show here, Z4 we show here. Sorry, with Z6, right? On the Z6, okay, we showed here, it has projection figures on the x, okay, is 3, and projection figures on the y is 3. So how to combine these two together into one, okay, figures? That's the we use in the constant number forms. We can define the y axis be represented by using a special symbols j, and the j has been defined as the root minus 1, which is the imaginary numbers. So we can define the y-axis as the imaginary numbers and the x as the real numbers. So the imaginary numbers has been symbolized with the root 1. Okay, so okay, so we introduce a symbol of the imaginary numbers, which defined as a root minus 1. In practice, we have not right, so root minus 1. So we have imaginary numbers of it, which is not real numbers. So then we can distinguish between the y-axis and the x-axis. So in contrast, we define the x-axis with the real numbers. So this is the real numbers. Okay, so we define the numbers on the y-axis as imaginary number symbolized by the j or I in some books. We define the numbers on the x-axis as the real numbers, which is a normal number. Then we can write the point in the xy plane as shown here. This is the complex Okay, So for each the point in the play, so complex number form of a point in a play can be written into like this, okay, with the x numbers as the real numbers and the y numbers as the imagined numbers, which symbolized by the j. Okay, so this is the point in the play, and you know that for a point in a play, it also can be represented by using the pointer forms. For example, the point B here, So it may have a so we say we have vectors in the plane which has a values r with the angle theta. Okay, so we have one of vectors in the xy plane. So we say the vector is b. It has an amplitude from the point, from the origins to the point. Okay, origin to the point. So which has the values r, and meanwhile it has angles to the x-axis, which is theta. So this is the polar forms of a vector. Okay. Okay, so you look at, so figure B2, it's a polar form of a point, or we say a vector on a plane. Okay. So now you can looking at the coordinate here, one can easily find out the relationships between the polar forms and complex number forms. Okay, so later on we have summaries on it. So we have the complex number form expressions of point. We also have the polar forms, polar forms on the point, of a point in the plane. Okay, so now we come to the relationship. Okay, so the relationship between a point, in a plane between the complex number form and the polar form. It can be easily brought into like this. Okay, you just looking at the relationship by comparison the figures B1 and the figures B2. One can quickly find out for a given vectors or with a point in a play. So suppose the point in a play represented by the Z, complex number Z, which has the real part x as the imaginary part y. If its amplitude is r, so the real part actually is the amplitude r times cosine theta, and the imaginary part is the amplitude times the sine theta. Theta here is the angles between the vectors to the x-axis. Okay, as a relationship, you can prove it. It's straightforward relationships. So you can further write to check about relationship on the figures B3. B3 here is the relationship between a polar form, complex number forms, and so on. Anyway, so you can write complex number forms in different way. The Poynter forms, the complex number forms. Furthermore, you can write it into the explanation row. Okay. Here is the relationship between the complex number forms and exponential forms, and also the Poynter forms. Okay, so for given complex numbers z, complex number z, okay, so that suppose we have the z in a plane and show in figures B3, which has a x, okay, on the x-axis has a projection x, on the y-axis has a projection y. It has a leg from the origins to the point is r, with the angle between the vectors from the origin to the point to the axis of x as angle theta. Then its complex number form is r times cosine theta plus j r sine theta. J is the symbol of the imaginary parts. Or you can write it into the exponential form. So the exponential form with the amplitude of the values r and the e, j, theta power. Okay. Or you can write into z equal to the r, which represents the amplitude and angle theta. Okay. So in general, you can just use the one z, bold z, to represent a complex number forms. Okay. Z represent. Or you can write into the complex number forms and show here, or Poynter forms, or exponential forms. Okay. So in the left of these chapters, sometimes using the complex number, we just use a complex number represent the voltage, current, or impedance. Or we write it into the complex number forms, complex forms with two terms. One is the real part, the other one is imaginary part. Or sometimes we write into the exponential form. Sometimes we write into the Poynter forms. Okay. Depends on case by case. Okay. So in the following sessions, that it shows that how to do the calculations about complex number forms. The first one is the sum or difference of two complex numbers. Example B1, given that we have two complex numbers. So the first one is the Z1, which is 5 minus J2. And the second one is the Z2, which is minus 3, okay, minus 3, okay, minus J8. Minus J8. So then the Z1 plus Z2, the sum of them is simply the direct sum of each of the parts. Okay, the real parts, the sum of the real parts, and the sum of the imaginary parts. The difference, of course, is the same for the two complex numbers. Okay, their difference is their real parts difference plus their imaginary parts difference. So very straightforward. So this is applicable to all constant number forms. If you have a term constant number forms added together, or the difference between them, you can follow the same rules to the calculation. Okay. Now the multiplications or divisions, multiplications. So here is the multiplications. Suppose you have two constant number forms. So the Z1 and the Z2. The Z1 has amplitude R1 with a phase angle θ1. The Z2 has amplitude R2 with an angle θ2. Then their multiplications is simply that their amplitude multiplications and their angles added together. So very convenient for the exponential forms. Similarly, their multiplications in polar forms is very straightforward. Okay, so if we have two constant numbers that written in polar forms, their multiplications is the amplitude of multiplications. Their angles is the sum of their angles. Or if you're doing calculations using the complex forms, again here, if the Z1 so has the complex forms x1 plus jy1, and the Z2 has the complex forms that is x2 plus jy2, then you should follow the multiplication rules to do the calculations for both the real parts and imaginary parts. You will find that the calculations is a little bit complicated. Okay. Okay, you will find that if you're using the polar forms or exponential forms for the multiplication, it is simple. If you're using the complex forms to do the calculation of the multiplication, it is complicated. Okay. Therefore, in practice, before doing the multiplications, you can change a complex number into the polar forms or the exponential forms, then do the calculations. Okay. For getting sum or difference of several complex numbers, you had better write them into okay. So for getting sum or difference of several complex numbers, so you had better write them into complex form before the calculation. Similarly, for getting multiplication of several complex numbers, you can better write them in polar form before doing the calculation. Okay, so if you have several complex numbers that you would like to calculate the multiplications, you had better write them into the polar forms before doing the calculations. So this will make the calculation be more simple and straightforward. Okay? You will not longer making mistakes during the calculations. Okay, so that's some suggestions. Okay, some suggestions. Okay, similarly, okay, so for the divisions, next slide about divisions, sorry. So in using the polar forms, okay, for two complex numbers, okay, in the polar forms, it is straightforward. Polar forms, exponential forms, straightforward. Okay, so this is very similar to that for the multiplications. So once again, if you have several complex number forms, complex numbers, and you would like to do the divisions, you had better write them into the polar forms before doing the calculations. This will making the calculation straightforward and simple, and you avoid to make mistakes. Of course, you can do in the calculations using the complex numbers forms, which will making the calculation more complicated. So very complicated. Very complicated. Okay, so this will may lead to some mistakes during the calculations. Okay, so for these calculation rules, so here we have several examples. B1 example, B5, B6, B7, so which is simply calculations using the formulas given above. Okay, no more special issues to explain. So the last point is about to conjugate a complex number forms. So we define the conjugate of a complex numbers. So suppose we have a complex number z, which is written into x plus jy. Its complex number form, right? The conjugate is defined as this. Okay, so we have a complex number z. Its conjugate we write into z star, right, mark. So its original form is x plus jy. Its conjugate form is x minus j1. So as a result, the real part can be found by the combination of the original z and the conjugate z star, and so on. One can easily prove these issues. And using the same definitions, if you write the conjugate into the polar forms, then you will find that if the original exponential form is r e j theta, its conjugate will be r e minus j theta. Similarly, if its polar form is r with the angle theta, its conjugate polar form will be r with the minus theta. Furthermore, if it is a triangle forms, if the original one Z is R cosine theta plus J sin theta, then its conjugate will be R cosine theta minus J sin theta. Okay. As a result, so its conjugate will be itself. And meantime, two complex numbers, the products of two complex numbers, okay, its right products conjugate is the conjugate products. Okay, the sum conjugates is the conjugate's sum. Okay, two complex numbers by division conjugate is the conjugate division, right? Conjugate division. All this based on the definition and the complication rules of number forms. Okay, so today we are focused is that the definition of the effective values of a periodical function and the calculation rules of the complex number forms. So remember the relationship between the Poynter forms, complex forms, and the exponential forms, the relationships for complex numbers, so which will be frequently used in the AC circuit analysis. Okay, so today actually is fundamental knowledge learning. So that's the end of today's tutorial session.